This is talk about C sharp because they're all tools. C sharp is a doddle, but the people who are not familiar with the word doddle or can't make out what the picture on the background is, that's not a slice of cheese, it's a piece of cake. And for the people that know me, they'll realise that there's a certain amount of irony in the title. What I'm going to talk about is some of the niggles in C sharp and why it's not as simple as I think it is. So, the C sharp standard, or the language spec, describes C sharp as simple programming, simple as other people say. The thing about simple is, and C sharp is a pretty good programming language. It's been used in a variety of big production scenarios for quite a lot of years. And the thing about worthwhile things is they're often complex, reasonably complex, and for good reason. And that's what makes them worthwhile. The problem with complexity is that ends up introducing, as we'll discover, some special cases in the language to cope with certain scenarios that possibly weren't originally envisaged in the language as it first developed. So C sharp 1 was pretty much 21 years ago, 2002. And there are some common kind of misconceptions of C sharp from the beginning, and things that weren't quite introduced correctly or for whatever reason or that caused program confusion. And there are, over the years, and actually with increasing rapidity over the last 5 years or so, new features being added to the language which has had a certain amount of impact on how what the original C sharp, if you want to call it that, classic C sharp, looked like. So one of those things is loop variables. So is everybody in the room reasonably familiar with C sharp syntax? Can anybody not? Okay, good. This is a reasonably classic example of how things have changed in C sharp. Here we've got a for each loop, which is a fairly basic construct for going over the elements of a range or sequence. And here we're creating new tasks, which may be separate threads, but that's a different discussion, that's kind of not the point. The really important thing is this lambda, which is a function-like object that's capturing an outer variable. And I suppose the question is, do we think that that test should pass? What we're doing at the end is we're taking the first element of the sequence, calling the lambda, and coming back with the answer that it gives. Now this is, what version of the language does this test pass in is the real question, because the behaviour of this code changed. Where the captured variable, the mechanics for a captured variable or a closure is that the compiler introduces a class to capture the variable as a field in that hidden class. By the time you get to the end of the loop, the variable that's been captured has been updated to the same value each time. And so what you actually get at the end of the day, because we've got a sequence of 4 elements, is that the value at start as the captured variable would end up being 5 for all of the tasks. Anyway, programmers find that very confusing, so the language designer changed the behaviour. So instead of creating a single closure object for the whole loop, they create a different closure object for each time around the loop. And so the test does indeed pass. Watch carefully as I flip slides and spot the difference. Anybody not see it? All we've done is swap the for each loop for an ordinary for loop, which goes through. This has what was the old behaviour of the for each loop. And this test doesn't pass, whereas the one prior to it does, in modern C sharp. So this change, that behaviour of the for each loop changed in C sharp 5, which was in 2012, I think, so 10 years ago. Still a question that I see arising. Somewhere, I put my water in, I don't know. But the fact that the language designers special case the for each behaviour so that it would meet these programmers' expectations. And the difficulty with that is that there is still a language construct. that exhibits what many programmers think is erroneous behaviour. And is in fact still the source of bug reports Microsoft also the Roswell team, the compiler team. There are better ways of doing this with the libraries anyway, where we don't use any loops, and we just use link facilities to create new tasks. And that behaves as most programmers expect in any case. But my point here isn't really about for each or for loops or whether it's good or bad behavior. It's about the fact that there is a special case in the language. The evolution of the language meant that that special case had to be introduced, and it's specifically called out in the language spec that the for each loop behaves the way it does. So, over time, you get new hazards and anomalies in any language that evolves. That is, if it's useful, then it's probably not as simple as it describes itself as being. But you introduce new little warts, if you like, of the way things behave. And so you get new hazards to avoid, and new ways of thinking about how to use the language, which means you have to pay attention. As the language versions go up, there are new things to look into. Let's say about all these behaviors that can you got. So, overloading operators is something that C# has supported since it began. It was one of the things at the time that set it apart from Java, for example. And there's nothing wrong with this code. I'm not asking you to look for it. I hope there's nothing particular. This is just to set the scene. Because of the way that the C# language began, it made this distinction between value types and reference types, which is one of the other big distinctions from Java. And the struct, which is a value type in C# terminology, has, although things can be compared with equals, everything can in C# because object is the base class that defines it, object is the base class of everything. The struct implementation of that, the default one, might not be optimal for various reasons that we're not going to go into here. But the basis of defining equality for yourself is this, where you have an I-equitable interface which allows you to create a type safe equals method, which is that first one, and then you override equals from the object-based class for reasons, and then you also implement get hash code to make sure that behavior matches. There's this idea that get hash code and equals being defined on the object as the base class of everything is a language design problem. I think it is, but we're not going to go into that either. What we can also do is overload the equality operators, equals equals and not equals. So one of the things about C# is if you overload one of those, you have to write the other. If you don't do both, the compiler tells you with an error, fails to compile your code. Well, okay, so equals equals is a direct map to calling the equals method, not equals. The only reasonable way of implementing it is to do the opposite thing. I hope everyone spotted it, but it's easy to miss. Forcing you down that path of having to write that is just a way of introducing errors. The compiler must know that not equals should be the opposite of equals, and frankly doing anything other than that, I'm just saying, it wouldn't pass a code review for me. But why can't the compiler just do the right thing? Well, the answer is it can, and we're going to look at some examples of what the compiler can do and can't do. Over the last 20 years, the C# compilers got very sophisticated in the code we have generated for. 20 years ago, they were, I think, probably trying to get a version out as quickly as they could, and they didn't put that in, they just left it up to the programmer. But it's an opportunity for the programmer to introduce errors. So a good example of this is learnable value types, which, so these were introduced, I think, in probably C# 2 in the support group, I can't remember. And the idea is that you can have a value type that has, or you can have a value that doesn't have a value. It's effectively null. So because of this difference between reference types and value types can't have the value null because they're not that's only applicable to references. So we've got the idea of the nullable value type, which on the face of it is introduced to support things like the SQL version of values, where you can have a value or not a value, can be null in database terms. But it turns out that there are other uses for nullable value types as well. And it's this idea of being able to represent an invalid value without having to pick one of the valid values as an edge condition, -1 for is perfectly valid, isn't it? Trying to use that as a flag. It's probably not applicable to all domains. So nullable value types are useful from that point of view. But this comparison at the bottom, red is not equal to blue. That's code that's generated by the compiler. So the compiler won't generate an operator not equals for your struct answer, but it will, in a later version of the compiler, obviously the original one, allow you to compare nullable value types with equals, equals, and not equals operators, as long as the underlying type has those operators defined. And this is a technique called lifting. And it looks a little bit like this. So nullable value types they're an actual type, and the little question mark syntax is translated by the compiler to this. So in the comments, I've got my original code with the equivalent that is generated by the compiler for those things. So when you type color question mark red, you get a nullable color, which is a system-defined struct. And so we create the red value and the blue value, and when we compare them together, this nullable color type doesn't have these operators defined. What the compiler does is it rewrites that not equals expression and lifts the implementation of our definition of the operator for color of fixed from the earlier version, right? And just puts it in line where I had the original expression. So that's one example of how the compiler can inspect the code that you write, inject correct code in the right way, and save you having to write your own boilerplate in the same sort of fashion. And because nullable value types can have a valid value or a valid value, then a comparison involving the nullable value type means that if they both have no value, then they're equal. If only one of them has a value, then they're not equal. And then you then have to check that the real value that they both have is equal or not. And that's what this code is doing in a pretty efficient manner. So really briefly, the algorithm says if the nullable type allows you to query whether it has a value or not. If those things are different, then they're not equal. So if one has a value and one doesn't, then it's not equal. Otherwise, we use get value or default because it's alternative with me throwing it and catching an exception. The default values would be fine, and it's an example of why the default value is different from an invalid value, for example. So we can overload on nullable value types for struct types or record struct types. It's kind of the same story, but record struct in very modern C# are the same as structs with compiler smarts. This code wouldn't compile if our color type was a class. So in C#, nullable reference types were introduced with the same syntax as nullable value types, which have been long-standing in the language. The problem is that a nullable, as we saw in the previous on this slide, nullable value types are underpinned by an actual type called nullable. Nullable reference types are just an indicator to the compiler to use for static analysis. There is no type underpinning it. So it's not allowed. Sorry. If we do overload it for a struct type, then the compiler will prefer our one instead of the compiler generated code. But if it's a reference type, you get different behavior. So having this disparity in the language is just another opportunity for confusion and possibly introducing errors. Because you need to understand the reasonably arcane corner of the language in order to make it do the right thing. So a slightly more egregious example of that is parameterless constructors. So historically, this code would not compile because our log entry type is a struct. You were not allowed to write your own parameterless constructor. So all struct types can be default initialized by passing them arguments to a constructor, and you were not allowed to change that behavior for well, efficiency reasons probably. The idea being that you don't want to call a user-defined constructor, for example, when you're creating an array of elements or something like that. C#10, which is quite about a year old now, introduced the idea of being able to write your own parameterless constructor for a struct type and make it do the right thing. And you might want to do this, for example, if your struct type has a reference type field or property and you want to guard against it being null. It's perfectly reasonable thing to do. It's probably a good example of defensive programming to try and avoid the number of null reference exceptions that the users of the type that you've spent so much time carefully crafting. And aside, kind of almost a side effect of allowing default or parameterless constructors as opposed to default constructors. So there is a distinction in C#. For anybody that knows C++, there's a very there's a default construction and parameterless construction. There's a very specific difference between the two. There is in C# too. It's just that difference is different. As well as allowing parameterless constructors in modern C#, we can have property initializers. So like defining your own parameterless constructor, this was also historically not allowed for struct types. So property initializers and field initializers as well were introduced they've been allowed for class types for many versions, but not for struct types. Because these types of initializers where we've got, for example, the message property here, we're saying that it's initially assigned to the string.empty, and that initialization at the end is conceptually part of construction. So we've moved the initialization of those properties out of the parameterless constructor definition, but made them property initialized. We have to keep the parameterless constructor definition. And because the property initializers are part of construction, if we now, even though we have a parameterless constructor, we create a default instance of the log entry, we've still got null for our message properties. And that is the difference between default construction, or default initialization, I think is actually the term, and parameterless construction. So this, creating a default, doesn't call our parameterless constructor any of that. It doesn't call the parameterless constructor or the property initializer. A default value type is still just a default initialized value type. So this is important in as much as you can create an array of these types, and they are default initialized, they are not parameterless constructed. It's also important in generics where you want to be able to create default instances because, for example, you might not know what constructors are available. So this is an example where an apparently useful thing has been introduced into the language, and it is useful, don't get me wrong, I think it's a great idea. It's just that some of the original language rules interfere with it in ways that might cause surprising behaviour. So record structs is an extension of this idea. Record structs they were also introduced in C#10. So C#9 introduced the idea of a record, which is it's a reference type that has built-in value-like semantics. Don't want to get too much into that. Anybody completely confused by those words? That's a very long story. But record struct, it's just a kind of a symmetry to allow the same sort of compact syntax. So this record struct is, instead of a type between curly brackets that has all of the definitions that we saw for our colour type earlier, for example, we're passing positional parameters to the type, and between the parentheses at the end, the message. So the message and timestamp parameters to the type end up being parameters to the constructor. So we just demonstrated that I'm using some named arguments to create an instance of this type to show that the parameter names match the names that are given to the positional parameters at the top. We get properties of those names demonstrated here, what we call the message, and it is exactly using who you would expect. The compiler will generate the overridden equals method, the type safe equals method, the implementation of equitable log entry, and a bunch of other stuff, including get hash code. All has the correct behavior. It's really good. And this test passes. And I'm really pleased about that. It's really nice compact syntax for creating really quite sophisticated value types. So we can use our own properties. And by defining our own properties, message and timestamp, we inhibit what is created by the compiler. Because, okay, the ones created by the compiler won't do that null validation. They won't. It will just default initialize the message property to its default value, which is null. And we also string.empty to reduce the number of null exceptions that our users get. So here we create a new instance of this new package. Well, that's a bit interesting. Anybody like to suggest why that might be? Okay, really briefly, it's because we haven't created our own parameterless constructor for log entry. The compiler has generated one that takes a string in the datetime. It hasn't generated a parameterless constructor. The property initializers are not invoked when we call the parameters, because this isn't calling a parameterless constructor. That's just default initialization. It's not calling any constructors at all. Now that, I think, is egregious. I think that is a big hole for programmers to fall into. And that will just throw an exception at runtime. So that's it. You don't get any compiler warning. You don't get any message from the compiler about this code. It compiles this just fine, but it goes bang at runtime. And I think that's a hole in the language design. This doesn't apply to plain record types, which are reference types. In that case, this comes for a record. So we take out read-only and struct, and we just have a public record log entry, or C record, actually, for good practice reading. This code won't compile. And the reason for that is records are reference types, and when you write your own constructor, the parameterless constructor is inhibited. The compiler doesn't generate it, you have to write your own if you want that behavior. Because we are using the positional parameter syntax, even though the compiler has generated the constructor that takes those parameters, that's considered to be a user-defined constructor, and therefore inhibits the parameterless constructor, or the default constructor, for a record. So, if it's just a record, code doesn't compile. If it's a record struct, code goes back runtime. Okay. Don't get me wrong, I think there's quite a lot to like about records and record structs, but Again, we're talking about special cases in language design. So we don't get I've forgotten what this slide's meant. Okay, time. Slide's too short, skipping over it. On to the next bit, exception safety. So one of the things that C# did differently from the languages that went before it, in many ways, is how it manages exception safety, or particularly lifetime. So this is really about garbage collection rather than exception safety per se. But what I've got, just really quickly, I've got two disposable types going on here. Well, actually three disposable types. The out broke boot disposable. Just kind of imagine what the types of these look like. They are disposable. And I dispose has been, from the very beginning of C#, a kind of some way of manually managing the lifetime of objects in memory. Memory is, okay, it's about lifetime, not memory, but the point being that you can try to have some kind of deterministic action that goes on by explicitly saying, I no longer want this object in memory. And here we're saying that when we call dispose on a breadth object that contains these two other things, that those two other things will be automatically disposed. So it doesn't mean they go out of memory, it just means that we are manually saying that those either, that the owning object is going away. But there is there is a really well-known problem with this kind of pattern, where if constructing the sync object were to throw an exception, the previously constructed source object leaks, in effect. Depending on, it may be that that's completely benign. It might be that it's holding on to some kind of system handle that needs to be disposed and therefore leaked. So, a couple of approaches to this.
Excuse me, what do you mean by leak?
Sorry?
What do you mean by
Leaks.
leak?
So, when you acquire a resource, say it's an operating system resource that's expensive to hold, you want to be able to say that you've finished with it before your program ends. So the classic example of this is memory, where you acquire a piece of memory and then you release it back when you finish with it. This is what garbage collection handles in C# and Java doesn't explicitly handle in languages like C or C++. Garbage collection only does the memory side. It won't do other system resources, such as, say, Windows handles. And if you don't release it back to the operating system, it's regarded as leaked, it's lost.
Okay.
And so it's good practice. As soon as you're finished with a resource like that, you tell the operating system we don't need it anymore, and it can be reused for something else. But if you say you create thousands of Windows handles and you don't release them in a long-running program, then certainly in Windows you run out of handles. Or program crashes and they will get released back to the operating system. But there's one approach to garbage collection. So the way, kind of the big manual way of handling this is by try and catch. So we try to create the new sync. If it throws an exception, then we manually dispose of the source object, and that's fine. I mean, it's okay when you've got two objects. If you put three, then this becomes three, and you get more than three, it's mad. And it's how it comes. So we might think that C# has a built-in facility for automatically putting block management around that I dispose lifetime management thing with a using. And I can't remember what version, this is quite new as well, it might be C# 9 or 8 or 9, where a using statement rather than a using block with curly braces. And the idea being that that temp variable has dispose called at the end of whatever block it's already inside, whether that's a method or a loop or whatever it is. And so we might think that we can say, okay, we're going to manage the lifetime of temp with a using statement, and then we create our sync, If that throws an exception, then we go out of the block, temp has disposal called on it. Otherwise, we assign our source field, as it was, to whatever temp was. Well, firstly, that won't work. But it also doesn't compile. So the first one will compile. What will happen is the temp will go out of scope, have dispose called on it, and that will, because source and temp are references to the same object, so you can dispose of source as well. And then we don't know. So we might think we just temp to null before it, you're not allowed to do that because temp is not there. And so we compile it. This does fail to compile, which is just a bit unfortunate. So lifetime management is just not as simple as it looks. So instead, we can create an object that will do the object management, the lifetime management. And here, what we're saying is that we're creating this owner type is also disposable and will dispose its own field, whatever it is. And then we can do what we were trying to do before. So instead of assigning source to temp, we're just calling acquire on the owner object. And the idea of that is that it swaps out what it was really doing and gives it back to you. And then when it itself is disposed, it doesn't do anything because it's got nothing to dispose. It's good. It's not part of the standard library. I wish it were, but it's not very hard. So the idea here is that we own an object and we dispose of an object when it's disposed. And then when we acquire the object, we can do this really neat trick. So C#7, I think, introduced the value tuple, which has this really nice facility of allowing you to swap one thing for its corresponding object like this. So here we're saying we're creating a variable called temp as part of this tuple. And so temp gets assigned to owned. Owned gets assigned to default, which is for a reference type, it's going to be null. And then we return the new temp object. Owned has gone away. So when we dispose, owned isn't there anymore. So we're using null coalescing, null conditional. Say if owned is null, don't do anything, otherwise dispose of it. And then if this gets disposed because of an exception in the other variable being assigned, then this will not be called, and we're still disposing of it. Simple lifetime management, opportunity for error. I wish the language would introduce something like this, rather than some weird things that they introduce. More smarts for that class. Not enough time. One thing that has been introduced in C#11, which is the most recent one, is the idea of this is specification mill. Sorry, generic operators. Historically not allowed. If you've got a method where you're doing some arithmetic operations between some values, you can't do it with generics. That's where you might do that. Target state is we want a generic method that will allow you to do all of those operators. They've introduced the facility to do that in C#11, but it's a bit mad. So we've got a lot of system interfaces that we can implement to say that we support addition, we support subtraction, support division in the type of T, the generic type that you're passing in, and implementing those interfaces is, well, it's easy, but it becomes really verbose. So we've got the facility to do generic arithmetic, but at a real cost of what the programmer actually has to do to make that type of support. I'm sorry, I had to rush that because I've only got a couple of minutes left. It does allow generic comparisons, so that for reasons, introducing in generic types has been historically difficult. You've been able to compare with null, but not with anything else. So you might end up having a type that has to implement both the interface to support generic operations, so that's the I-equality operators thing, as well as being I-equitable and any of the other interfaces that we can swap. So this is brand new language features to address arguably what were already just shortcomings of the language. But what they've done is they've introduced something that's really actually quite complex to implement. C++ programmers are going, well, I don't understand why it doesn't just compile anyway. But that's a different story. What have we learned? That defining inequality is still easy to get wrong. Something you've had to do for 20 years, still easy to get wrong. Exception safety still not as easy as it might be. The compiler can generate lots of stuff on your behalf, but object initialization is more complex than ever. And C++ programmers are going, yeah, simple, isn't it? Record-to-record structure great, but they're not silver bullet. And generic arithmetic's here! But there's still no way to constrain a generic type to only have a constructor anything other than the prime material stuff. You can't say, for example, that I want T to have a constructor that takes a string and takes time. And that's the thing I've been wanting since C#2. But instead they gave me generic arithmetic.